In this Mathematica Sessions video on discrete math, this is number 11 and the final episode of the discrete math series. For now, we're going to look at more combinatorics and graph theory. So if you're interested in that, keep watching. Hi, Jason. Okay, guys, let's begin this. So we've got a number of questions in this problem set. Most are on counting, but we've got some applications of set theory in counting and a number of other things. So let's start beginning. So the first question says, what is the coefficient in or of x to the, that should say of, and it looks like I copied and paste that, coefficient of x to the fourth in 2 plus 3x to the power of 7. Okay, now of course you can just expand this out, but that's a bad idea. You want to be able to do this by hand quickly. So we've got this formula right here that a plus b to the power of n is the sum of binomial symbols times a to the power of n minus r times b to the power of r. So that's n plus 1 terms. Okay, and so if we substitute in here that a is equal to 2 and b is equal to 3x, n is equal to 7, well, let's have a look at what this looks like. So the n is 7 in this case, so we'll put 7 everywhere we see n. The a is 2, and the b is 3x. Okay, and what we want to know is what is the coefficient of x to the power of 4. So we need to work out what the value of r is, and we can clearly see that when r is 4, we have an x to the 4 there in that term. So let's just say if r is equal to 4, r equals 4, then what we're looking at is power of 4 there, power of 4 there, 4 there in our binomial symbol. Okay, so we want to simplify this and look at the actual coefficient. So the coefficient is the number next to the x. So just write that this is equal to this number multiplied by x to the 4th, of course. So coefficient, we'll stop there, is the actual number next to it. Okay, and now let's calculate this. Now, you know how to calculate binomial symbols, how to calculate powers. So I'll turn all of this into a comment, and then I'll just get the computer to help out with this. Okay, so I'll copy this, but I've used a vector to denote 7 choose 4. It's actually, in this language, it's just binomial. I write binomial, then I put 7, comma 4, and then the rest are fine. The syntax is okay to run that. Okay, and we got 22680. And of course, you can do that easily by hand. And so I'll just take that and I'll put it up here and say that simplifies to 22680. Any questions? Okay, guys, let's have a look at the next one. So the next one says, what is the coefficient of x to the 12th in 3 minus x cubed all to the power of 6? Okay, so now that we clearly know what the coefficients look like, so I'll just copy out the this part of where a is equal to 3 and n is equal to 6. Oops, 6, and then b is equal to minus x cubed, so just copy and paste that. right, and we want to know what the coefficient of x to the 12th is. So let's just say equals c times x to the 12th. And so we need to know the value of r. So if we expand this part of it out, we have minus x to the power of 3r, right? So minus 1 to the power of r really times x to the power of 3r. So what we're looking at here then is 3r is equal to 12, and we want to solve this, right? Solution's clear. Divide by 3 and you get r is equal to 4. Okay, so now we can just use that and work out what the coefficient is. So now 4 is even, so we don't have to worry about the minus 1, because minus 1 to the power of 4 is 1. And in fact, we're interested in the coefficient, so we just calculate this with r equal to 4. Okay, and so I'll just use some code to do that. Again, and I'll make the rest into a comment. So we're looking at 6, choose 4 times 3 to the power of 2. And I think maybe I should put a star in there to multiply. I don't think I need it, but let's do it anyway. And we'll turn this part into a comment so that we can run this. And we get 135. So I'll take this and I'll copy and paste it into this spot. So this is equal to 135. All right, good. Let's have a look at the next one then. What is the coefficient of x to the 8th in 3 minus x cubed to the power of 6? Okay, so what we need here is this again. And let's just fill things in. So we've got a is 3, n is 6, b is minus x cubed. Okay, so we want to know first, what is the value of r? So let's say that this is equal to some number times to the power of 8. But if you look at this, we need x to the power of 3r is equal to x to the power of 8. In other words, we've got to solve 3r equal to 8, but the solution is not an integer, right? The solution is not an integer. So then what's the coefficient, right? Because we know that if we take the sum of these, they're going to be integers because we sum over integers. So since the value of r is not an integer, well, then we find out the coefficient must be equal to 0. In other words, it's just not there, right? Okay, next problem. How many integers between 1 and 600 inclusive are co-prime with 15? So co-prime means that the GCD is equal to 1. So let's just rephrase this. So number of integers n such that 1 is greater or equal to n and less than or equal to 600, and that the GCD of n with 15 is equal to 1. So that's really what we're looking for here. Okay, but we want to expand the, that GN with 15 is equal to 1, because we can get a little bit more, I guess. I was going to say more specific, but it's not, it's just equivalent to. So let's rephrase this again and say this is the number of n between 1 and 600 such that the GCD of n with 3 is equal to 1, and that's equal to the GCD of n with 5, right? Because 15 is 3 times 5, and 3 and 5 are relatively prime, meaning that their GCD is 1. And so this is equivalent to the GCD of n with 3 is equal to 1, and the GCD of n with 5 is equal to 1. All right, so that makes things a little bit simpler to look at. All right, so let's consider now bases. what are the numbers between 1 and 600 that are divisible by 3? Okay, in other words, not satisfying GCD n with 3 equal to 1. So we've got 3, we have 6, we have 9, and so on, up to 600. Okay, so so those are the numbers that are divisible by 3 in that range. And how many are there? Well, you can just consider this as a collection. Each of those are divisible by 3. So let me just show you how to think this as a set. Okay, so we've got this set, and then that set, I guess let's call it a vector, okay, so I can do what I'm about to do. Factor the 3 out of this vector, and then the last one's 200, okay, so these two are equal. Now, this clearly tells you how many you've got, right? You've got the numbers 1 to 200, and so there are 200 of these. So let's say 200 of these, and let's say that, and rephrase what this means, that the GCD of n with 3 is greater than 1. Okay, now let's look at the next case. And so the next case, something like this, except for we're considering the number satisfying GCD n with 5 is not equal to 1. So in this case, we've got 5, 10, 15, and so on to 600. And we can apply the same trick, factorize out. And so we have 5 times 1, 2, 3, and so on up to, let's see, what is 600 divided by 5? Well, 600 divided by 10 is 60, right? And so if I divide by another 5, that's the same as multiplying by 2. So I've got 120 of these, right? Okay. Where are we? Okay, so 120 of these. So I want to say, so something like this. So copy and paste. So 120 in this case, where the GCD of n with 5 is greater than 1. All right, but there's an intersection here, right? Because we also want to count the ones that are divisible by 15. So let's discuss those as well. So the ones that are divisible by 15, well, we've got 15, we've got 30, we've got 45, up to 600. And if we factorize the 15 out, then we've got 1, 2, 3, and so on. And we stop at 600 divided by 15, which is 40. And so there are 40 of these with GCD of n and 15 greater than 1. All right, so now what we want to know, all right, so let's call this A, let's call this B, and then let's call this one A and B. Okay, so A and B. But what I mean by that is the intersection of those as sets. Okay, so I'll pull out a palette and find a button for the intersection so we can properly display that for you. Okay, A intersect B. And we have a nice formula for this, right? So what I want to know is how many are in A or B. So in other words, the number of elements in the union of A and B. All right, and so this is equal to the number of elements in A plus the number of elements in B minus the intersection. So the number of elements in A or B. That's the A and B. Okay, so now we can proceed to calculate this number. How many are in A or B. So that is then equal to, let's see, what have we got? 200 plus 120 minus 40, correct? Okay, so simplifying that, we have 320 minus 40 is 280. And now what we want to know is the total minus this. So the total is 600 minus number in A or B. So that's equal to 600 minus 280. And that looks like 320. All right, so let's just say then that what we've deduced is that the number of integers between 1 and 600 inclusive such that the GCD of n with 15 equal to 1 is 320. Okay, any questions there, guys? Righto, let's move on then. Okay, yeah, so the next one, explain why in a group of 50 people, at least 5 people were born in the same month. Well, this comes down to the pigeonhole principle, basically. So note that here, pigeon, and I hope I spell this right, pigeon, that's a tough one. Pigeonhole principle. Okay, so basically if you've got several boxes, say n boxes, and you have n plus 1 items to go in each of these boxes, one box has to have at least 2, right? Because you fill all the boxes, all the n boxes, and you have 1 left over, so you try to avoid putting it in a box that already has a pigeon. So, but you can't because you have all the boxes full. All right, so that's basically the pigeonhole principle, and that's what we'll use here. Okay, so if we've got 12 boxes being the months, then let's just draw these. So I've got box 2, box 3, and so on, right, up to box number 12. And so this is January, February, March, up to, what's the last month? December. Okay. So there are 12 of those, but how many pigeons do we have? 50 pigeons. Okay, so 50 pigeons going in 12 boxes. Now look, we try to avoid having 5 people in one pigeonhole, but yet we can't. Okay, so let me turn this into a comment here. So basically, let's do the calculation of 50 divided by 12. And what I want is a numerical estimate of this. So I put a decimal point. You need to put a comment around pigeonhole principle. Okay, let's just calculate that. You see we get 4.16. So basically, you go along and you put 4 pigeons in each of these 12 boxes. And you're left over with 2 pigeons that you have to put in one box, and so they all have 4 already, basically. So you're forced to put a pigeon in 2 boxes that already have 4 pigeons. So you're going to get one with at least 5 in it. So that's basically what we want to say here. But you can take the floor of this. All right, so the floor of 50 divided by 12, and you get 4, and then what you look at is 12 times 4 is 48, right? But you've got 50 minus that, tells you how many leftovers you have. In other words, quotient remainder theorem. So our remainder is, and so we've got 2 extra pigeons to put in boxes that already have 4. Okay, so I mean, I'm not writing it out by hand, but I hope I've explained that well enough. Let us know if you have any questions. Okay, so next one. How many people do you need to ensure that at least 7 people were born in the same month? All right, so what we need to think about is how do we avoid getting 7 in the same month? So what we want to look at is what makes that overflow. So 6 times 12 is 72. So if we had 72 people, then we could ensure that that we have 6, we can spread it out evenly and have 6 in each month, right? But if we have just one more than that, then we can't do that anymore. And so we have 73 people would be the least such number in order to ensure that at least 7 people were born in the same. Okay, next one. Show that if we select 6 distinct integers from the set 1 through 10, 2 of these must add up to 11. Okay, so again, we try to avoid getting 11, but what we want to think about is partitioning this collection. So I'm just going to build this right here. So we're at table J goes from 1 to 10. All right, so there's a set. And now what I want to do is break it into pairs. But in such a, all right, so I'm showing you some code here as well, right? You don't need to learn any of this about the code. I'm just showing you how I like to think about things in code too. So what I want to do is partition these into pairs such that the sums add up to 11. Okay, but I can see I want 1 to go with 10 and so on. So let's call this set T. All right, and then I'll say partition T into 2, break it in 2. Oh, hang on, I want 5. I want 5 first. Okay, there we go. And let's call this one A. Okay, now this is A right here. So I want to take the first one. So A, and take the second one. So I'll pull out the second one here first. Okay, so there's the second one. Now I want to reverse it. So I have to spell that right. Okay, so I've reversed that, and now let's call this one, what's a good name? W. Okay, I want another name for the first one. Let's say U is equal to the first one, which is just A1. All right, so I'm interested in these two, and let's comment out the rest. Now what I want to do is pair the 1 with the 10, the 2 with the 9, and so on. Okay, so I'll go U, J to pull out the jth one, and then I'll pair that with WJ. I'll make a pair out of these, and then I'll just list these from 1 to 5. Table J goes from 1 to 5. Okay, now I've got the partition that I wanted to get here, right? So I'll comment out everything except these two. All right, now what you should notice, because we constructed it so that the 2 of these always add up to 11, all right? Now our goal is to try to select 6 integers from the set of 1 to 10 so that 2 of these must add up to 11. All right, so let's try to avoid it here. So if we were to try to avoid this, I might take 1 from each, right? So in other words, I could choose 1, and then I might choose 2, and then I might choose 8, and then I might choose 4, and then I might choose 6, for example. Okay? So if I take a sum of 2 of these, I never get 11, right? But if I just take 6th one, I'm forced to take it from the other, right? So for example, if I took 1, I'm forced to take 10, for example, or 9, or 3, or 7, or 5, which would mean that they add up to 11, right? And so just in case I didn't say this properly, let's just read this. And maybe I need to resize that. Anyway, you could probably read it properly. So the set can be partitioned in this way. That's exactly what we did. So it says in order for a selection of distinct integers from the set A to not have 2 that add to give 11, at most one integer can be chosen from each of these subsets. However, there are only 5 subsets. So if 6 are chosen, must choose 2 integers from one of the subsets. And hence we have 2 integers that add to give 11. So I think I kind of said that, but in case I didn't, this is a good way to say it too. All right, so let's move on then. Question 4. All right, out of 100 people surveyed, 40 people like apples, 50 like bananas, 40 like cherries, 15 like apples and bananas, 16 like bananas and cherries, 17 like apples, and 10 people like all 3. So how many people do not like any of these fruits? Now look, if someone approached me in a pub and asked me this question, I would probably struggle because I wouldn't think instantly about what is the right tool to solve this, right? It would just say, it would just seem like a tricky question, right? And that it might seem like that to you, but fortunately we've got some easy mathematical skills to consider this. So what I'm going to show you here is some code for drawing some circles. So I'll just comment those out and I'll show you. Okay, so here I've got circles, right? So if you were going to consider how many are in the union of A, B, and C, this picture here might be helpful in recalling the formula for the number in the union of A and C. Okay, so let's begin to write this out. I guess I should do this down here. All right, so in other words, the number in the union of A, B, and C, and I need my symbol again for union. All right, so I'll just get intersection while I'm at it. And I'll just put those 2 symbols above so I can copy and paste them in. All right, so the number in the union of A, B, and C is equal to, now let's think about this. This is in all of these together, right? But we don't want to repeat them. We don't want to repeat counts that are in the intersection. So we take all of those in A, right? So all in A. So in other words, the number in A. Now, if we add to that the number in B, you see what we get is we count the intersection of A, B twice. Okay, so now in that we want to get rid of the number in A and B because we don't want to count that twice. Okay, now there's more to this, right? So now we add the number in C. Okay, but when we do that, we have counted some things twice again. All right, so in other words, we have counted twice the number in A and C, so the intersection. So we've got to subtract that. And we've counted twice the number in B and C. So we've got to subtract that away. But we've also done something unintended here because now we've done that 3 times. So now we've got to put back in the number of those in A, B, and C. Okay, so we've got to add that back in because we have taken that out too many times. So, so plus. And I need this symbol again. All right, so here's our formula, okay? And now, fortunately, we've got apples, bananas, and cherries, so which we can nicely abbreviate by A, B, C. So let's just enumerate what we have here. So 40 apples, 50 bananas, 40 cherries, okay? So this is 40, this one is 50, and C is 40. Okay, continuing, those that like apples and cherries, we have 17 of those. Those that like bananas and cherries, we have 16 of those. And then those that like, let's see, what we missed, apples and bananas is 15 of these. Okay, good. And then the intersection of all three, we know that that is, according to this, let's have a look, 10 people like all three. Okay, great. So that's 10. Okay, now we just want to substitute into this formula. So I should really put this above that. Okay, and then simplify this. So we've got 40 for this one. We've got 50 for this one. We have, in the intersection of A and B, we've got 15 to take away, and C is 40. Intersection of A and C is 17. And then we have B and C is 16. And then all three is 10. Okay, good. So I want to add all this up. I'm going to use the computer to do that, but I need to turn all of this into a comment. I'll put that there. And then let's copy and paste this. All up. Okay, we get 92. Great. So we'll say that this is equal to 92. Okay, now that we know that this is 92, so this says how many like apples or bananas or cherries, and the question is how many don't like any of these fruits. So what we want is 100 minus that then. Okay, so 100 minus 92, we can clearly see that that's 8. So let's say don't like those fruits. Okay, passion fruit is best. Okay, all right. For example, right? I find passion fruits, you can get good ones and bad ones, right? Sometimes they're amazing, but sometimes they taste kind of off. So maybe the rule is eat them when they're fresh. All right, so I'll save this and then let's have a look at the next question. The last one? No, second to last on this set. Okay, so this is about graph theory here. There's some pretty basic questions though. So we've got the question, let G, H, and K be the graphs below. So here I've just got them here. Answer yes or no the following questions and explain the answers. Okay, so the questions are here below. G is a simple graph, so true or false on this one. Okay, so a simple graph needs to have no loops or parallel edges. So in G, we see that it's got loops there and there, and there's also parallel edges, right? So this is an example of a parallel edge. So the answer here is no. No, and we say G has loops and parallel edges. Parallel edges. Okay. The next one says the sum of the degrees of the vertices of G is 18. Well, we can add them up, right? So let's just have a look and test that. All right, so the degree of V1 is 1, 2, 3, 4. So let's say sum of degrees is equal to 4 plus. All right, let's move on to E2. So we've got 1 plus 1 plus 1 plus 1. That's 4 plus 1 plus 1. That's 6, right? The thing is here that we want to count a loop as 2 more, right? 2 more than you had for the non-loop parts. So 1, 2 for the degree contribution that a loop adds. Okay, so that one is 6. Now let's have a look at V3. We've got 1, 2, 3, 4. So plus 4. And then V4 is plus 2. And then V5, 1, 2, 3, 4. Okay, and let's add these. So 4 and 6 is 10, plus 14, so 16, 20, right? 20, not equal to 18. Okay, so the answer here is no. False. Okay, next one. G contains an Euler circuit. So I've got the definition of this stuff. G contains an Euler circuit. An Euler path or trail is a walk through the graph which uses every edge exactly once. And an Euler circuit is an Euler path which starts and stops at the same vertex. But there's a theorem that says if G is connected and all the vertices have even degree, then such a circuit exists. Okay, so yes, G is connected. So let's say that. Yes, G is connected. And all vertices have even degree. So G contains an Euler circuit. Okay, next one is about the graph H. So H contains a trail. So what we need for that is we need the graph to be connected. We can see it is connected. All but 2 of the vertices here have even degree. So in other words, vertex 2, vertex 1, vertex 4, they have even degree. The other 2 have odd degrees. So we can just clearly see an Euler trail here that starts with V5, goes around counterclockwise, and ends at V3. All right. So what we want to note here is basically yes, connected, and all but 2 vertices have even degree. Okay, good. So that's all of the questions in question 5. Any questions, anyone? I'm going to clearly finish too early, so I guess that's okay because it's the last session for you guys, and that'll leave us time to talk about your assignments if you wanted to ask any about that, and I can give those back to you in the session as well. Okay, so the next one says, hang on, did I not ask the question properly? All right, so basically, does there exist, I should just say that here, okay. Does there exist a simple graph satisfying these things, okay? So the first one is 5 vertices with degrees 3, 3, 2, 2, and 2. Okay, so the key thing here is that the sum of the degrees is equal to 3 plus 3 plus 2 plus 2 plus 2. Now let's add these up, right? This is equal to 6 and 6. which is 12, and this is even. Okay, so remember that the, here, this is what I want to tell you. The sum of the degrees is equal to twice the number of edges. So let's put that here. Sum of the degrees is twice the number of edges. Okay, so the number of edges then should be 6. And in fact, yes, you can create such a graph, simple graph, and I've drawn one right here, but I better comment this stuff out before I run that. Okay, so let's execute that and have a look. So here's an example, and let's just see. Vertex A there has degree 2, B has degree 2, and D has degree 2. So good, so far so good. E and C both have degree 3. Okay, we've got 5 vertices, so that's exactly this recipe here. So yes, there does exist, and here it is. Or it's not unique, incidentally. You can draw several. Okay. Great, and so let's just count the number of edges as well. 1, 2, 3, 4, 5, 6. Okay, so 6 edges, and that agrees with this. So 6 edges we were looking for. Since 2 times 6 is 12. Okay, good. So let's have a look. Next one then. 7 vertices with degrees 4, 2, 3, 1, 1, 1, and 1. All right, so we should add up the sum of these. So 4 plus 2 plus 3 plus 1 plus 1 plus 1 plus 1. Let's see, this is 6, and 3 is 9, plus 1 more is 10, plus another 3 is 13. This is odd, and that's an odd number. And so since, again, let's go and quote this again. Where did it go? Sum of the degrees is twice the number of edges. Okay, so if that's true, then how many edges do we have? Well, it would have to be 13 divided by 2, right? But that's not an integer, so doesn't work with sum equal to 13. Okay, so no such graph exists here. No such graph exists. Okay, good. Now this next one says 5 vertices with degrees 5, 4, 3, 1, and 1. So if we have 5 vertices, but look at this, this one has degree 5. Okay, that can't exist, and I'll just show you why in this drawing here. So take this example here. The vertex A has degree 4, you see? And so if you try to add another edge to give that degree 5, then you get a problem. And that problem is that you end up with a double edge, which makes it not simple anymore. So let's just change this, all right? So I'll copy and paste below. And I'll show you. See, I hope Mathematica can do this, incidentally. I don't know if we can make double ones, but oh yeah, okay. So it's just changed the layout. But yeah, it's the same, but including on a double edge here, a parallel edge. Okay, so this one here has degree 5 there, but it's no longer simple. And so let's just say to be simple, no parallel edges allowed. Hang on, allowed. This spelling, right? Not out loud. Okay, so no parallel edges are allowed, meaning max degree should be 4, equal to 5 minus 1. Okay, so this one, a simple such graph does not exist. All right, good. So that finishes